Okay, the rest of section 3.4 deals with probably one of our first, very important applications of the derivative, understanding the derivative as an instantaneous rate of change. So what we're talking about in the rest of this section is motion along a line. In other words, motion along a straight line. So let's pretend we have this straight line represented by S, right? So S is any value along this straight line. And let's say we have a function of t that represents wherever we're at on this S axis. So just to kind of put this in perspective for you, pretend like I had S equals 0 somewhere right on here. S equals 60 over here, for example. I have a straight line between St. Augustine and Daytona. So imagine there's an exactly straight road between St. Augustine and Daytona that's 60 miles long. And f of t might be my position anywhere in that. Say I'm driving a car, right? So I would drive a car at a certain miles per hour. I might have to slow down for a traffic jam. I might have to speed up. It's whatever I'm doing in my car to get from St. Augustine to Daytona along this straight line. And that function of t, let's say we know exactly what it is somehow. Okay, so that's the type of motion I'm talking about. Now, the different things I want to talk about is displacement, which means how far from 0 I am. So in other words, where I'm at on this x-axis. Velocity, how fast the particle, so now assume like a particle or the car, whatever is moving. The speed of that particle or car, whatever I'm talking about. The acceleration of it, and then a thing called jerk, which I'll talk about. Okay? So the first is the velocity. Now, the velocity is the instantaneous rate of change of your position, right? You take a snapshot of the car driving down the road, boom, it's instantaneously going a certain velocity. The only difference between velocity and speed is that velocity will have a sign associated with it. So positive velocity would mean that I'm increasing my S, right? I'm increasing my position. So if St. Augustine were 0, and Daytona is 60, then if I'm going from St. Augustine to Daytona, I would have a positive velocity. If I was going from Daytona to St. Augustine, then I would have a negative velocity. Okay? Hopefully that makes some sense to you. But the velocity then, since it's the instantaneous rate of change of our position, is ds dt. So it's this definition, but really just understanding that it's ds dt. Okay? All right. Now, a little bit more understanding of velocity. So here you can see, like, I put the s-axis as the y-axis, okay? And t is just time. So in other words, how my position is changing with time. All right? So what's going on here is that I'm increasing my S, I'm increasing from 0 to whatever. So again, think of 0 as being St. Augustine, up here being Daytona. So I'm driving from St. Augustine to Daytona. So if this is my position function, where I'm at anywhere along this S-axis, based on what time it is, then notice that the rate of change, the instantaneous rate of change, is a positive tangent line, right? It's a positive slope here, so the velocity, the derivative of s with respect to t, the rate of change of the position, is positive. That means I'm increasing my s. If I were driving from Daytona back down to St. Augustine, where I called St. Augustine 0 and Daytona 60, then my derivative would be negative, right? Because I have a negative velocity, which means I'm decreasing my s and coming back to St. Augustine. And you can kind of see how that works, all right? Hopefully that makes sense. And like I said before, there's not much difference between speed and velocity. It's just that speed is the absolute value of velocity. Think of that as if somebody's talking to you, they say, I'm driving 60 miles per hour. That's their speed. They're not telling you which direction. They don't say, I'm driving positive 60 miles per hour or negative 60 miles per hour. So speed is just the absolute value of velocity. Okay? So, for example, let's say now I have a graph. This is no longer a graph of position. This is now the graph of the velocity. So I have some position function, but I've already taken its derivative. You don't see it. You just see the velocity function. Okay, so this is the velocity function. I'm trying to lead into understanding of acceleration at this point. Okay, So what I want you to understand is here I have velocity. So now think about what acceleration might be. Well, it's the rate of change of velocity, right? Usually you talk about speeding up or slowing down or accelerating versus decelerating. So acceleration is the instantaneous rate of change of velocity. So notice that if my velocity is increasing, right, I have a positive slope for velocity, I'm speeding up there. If I have a negative slope for velocity, that means my velocity is constant, right? A negative slope on the velocity curve means my velocity itself is constant, means I'm not accelerating or decelerating, right? I'm not accelerating or decelerating. I'm staying steady here. There's a zero acceleration, right? Because that would then think, so I'm leading into you understanding that the acceleration is a derivative of velocity. And then if I'm slowing down, notice that I have a negative rate of change, right? Negative tangent lines to my velocity curve, so my acceleration would be negative. Now notice the way you think about that is here I have a positive velocity, right? Velocity up here is positive, velocity down here is negative. Negative velocity just tells you which you're heading in the opposite direction, right? Remember that, okay? So, sorry about that. So velocity being positive, but its rate of change being negative means its acceleration would be negative. So when velocity is positive and its acceleration is negative, that means I'm slowing down. So when velocity and acceleration are opposite signs, they're doing the opposite of each other. Velocity positive, acceleration negative means I'm slowing down. Velocity positive with acceleration, the slope of velocity being positive means I'm speeding up. So always kind of put it that way to check the signs of the two. So notice down here my velocity is negative. That means I'm heading in the opposite direction. Okay, that's all it means is I'm heading in the opposite direction. Now my velocity is negative and the slope of my velocity curve is negative, right? Any slope along here is negative. So my velocity and acceleration are the same sign. That means I'm actually speeding up. Okay, again, try to put this in perspective. Here I'm going from St. Augustine to Daytona. First of all, I speed up for a while, then I drive a steady velocity. Then I'm still going positive velocity towards Daytona, but I'm starting to slow down so I can stop in Daytona. Now I turn around and I'm heading back towards St. Augustine, which means I have a negative velocity just based on the way I set up my axis. You know, St. Augustine was 0, Daytona was 60, so I have to go back from 60 back to 0, which means I'm driving a negative velocity. So my velocities are negative as I drive back to St. Augustine, but my acceleration at the beginning is negative, which means my acceleration negative, my velocity negative, I'm speeding up to a point where I kind of get to a max speed, but I start to slow down right away. I don't have a while where I go constant in this example. So I have no max speed here. I mean, I get to a max speed, but then I start to, my velocity is still negative, right? I'm still down here where my velocity itself is negative. All the velocity in here is negative. But now the slope of my tangent line to my velocity curve is positive. So my velocity is negative, my tangent, which acceleration is positive, means I'm slowing down. Okay, then I get back towards St. Augustine and I sit still for a while. I do nothing. I sit in St. Augustine for a while. My velocity is 0, my acceleration is 0 because it's a derivative velocity. I'm just sitting there in my car. And then at some point later, I say, let's take off. Okay, now this is t in seconds. I'm kind of putting it in a frame of mind for you, way more than seconds. But this is a particle moving along a curve. But I always like to use the St. Augustine Daytona example because it helps you understand the relationship between velocity and acceleration.